So record on this computer. So the goodness of fit test, guys, it's used to check whether a distribution, a certain given distribution, is still valid or not valid anymore. As I told you, the null hypothesis will be the distribution is as claimed, and the alternative hypothesis will be the distribution is not as claimed. What we use to solve goodness of fit problems, we use the chi-square distribution that looks like this. Starts at 0, it's always positive, it's skewed to the right. It's a family of curves. It will change with the degrees of freedom, with the size of the sample. So this is the distribution. It's not the bell-shaped, just distribution that you are used to. It's called the chi-square. We write it like this, chi-square distribution. It's always a positive because, as you notice, there is no negative. It starts at 0 and up. It is skewed to the right. And the shape of the curve depends on the sample size or the degrees of freedom. As the degrees of freedom increase, this shape will become more like a bell-shaped, curve. And in order to perform a goodness of fit test, guys, I told you that you need two sets of values. One is called the observed values that you will be given always, and the other one is the expected values that you have to find. Now, for the expected values, you will be given a percentages of each category, as you can see here. And then your job is to figure out a percent of the total for each one, and this is called your expected value. For example, here we have a sample size of 500, and he gives us those percentages. Type of violent crime, we have 4 categories. The observed values are given already. That will be given in a separate table, so you don't have to worry about them. But what you need to find are the expected values. So in order to find the expected values of murder right here, I put 60. And if you want to know where the 60 came from, guys, it's 12% times 500, which is 0.12 times 500 right here. This one will be 5% times 500, which is 25. This one will be 55% times 500. So it will be what, 275. This one will be 28% of 500, which is 140. And if you guys add those up, they should add up to 500. The O's will add up to 500. And the E's should add up to 500 as well. As you can see, I put sums here, 500 and 500. So we have 25 here. We have 275, and we have 140. And I did show you how to find the test statistic by hand. However, you won't have to do it by hand on the final exam. You can use your calculator. So if you use your calculator, you have to put this in L1 and that one in L2. And then after that, you have to run what we call goodness of fit test. Some students told me that they don't have it built on their calculator because they have an older operating system on the calculator. That is true. I did send you a link, however, to an app by Texas Instruments that you can install on your computer and use it. Or you can use StatCrunch. The process to do this by hand, guys, it's kind of tedious, but not difficult. So you just have now to do O minus E, which is 56 minus 60. And then you have to do 26 minus 25. Then 270 minus 275. I'm just going to do it just to show you how we can compute the test statistic by hand. 56 minus 60, guys, is -4. And then you have to square it, which is 16. This is 1 squared, which is 1. This is -5 squared. That's a -5. So 25. And 148 minus 40, guys, is 8 squared. 64. Now, the last step. O minus E squared divided by O. So you take this column and divide it by E. So this O minus E squared was 16. And what was the E here? 60, as you can see. So I just divide by 60. For this one, guys, it will be 1 divided by the E. What was the E here? 25. For this one will be 25 divided by the E. And what was it? 275. And that one is 8 divided by E, which is 140. And that's it. And your test statistic is the sum of all those values right here in the last column. So the test statistic is called chi-square equals the sum of the last column, which is going to be 16 over 60 plus 1 over 25 plus 25 over 275 plus 8 over 140. So this is how we do the work by hand to find the test statistic. Okay, now I'm just gonna go and do a couple more examples. So this is everything I talked about. The steps and how to find the test statistic are explained here, guys, so you can review this page. And for students who ask me about StatCrunch, here are the information how to use the StatCrunch to run a goodness of fit test. But for the calculator, this is what I'm going to be using today. Enter the observed values in L1, enter the expected values in L2, go to tests, goodness of fit test, enter the degrees of freedom. And the degrees of freedom, guys, is number of categories -1. Okay, I should put equal here. And then hit calculate. All right. And let's do this exercise together. We will be using technology for this exercise. If you have your calculator handy, guys, please have it ready so we can do this together. A teacher figures that final grades in the chemistry department are distributed as A, 25% of students get A, 25% get B, 40% get C, 5% get D, and 5% get F. At the end of randomly selected semesters, the following numbers of grades were recorded. Test the claim that the grade distribution for the department is different than expected. So we start. HO, distribution of grades is as expected, or as claimed, if you like. HA, distribution of grades is not as expected. And that's what he wants us to do, different from expected. So that's the claim. All right. So I'm going to be consistent with what I said earlier, guys. These are the O's. We're going to put them in L1. Now for the expected values, guys, help me find them. For A, for B, for C, for D, and for F. Okay. What was the percentage for A? It's 25%, as you can see. So we need to compute 25% of the total. He didn't give me the total, but what you can do, guys, you can add them up right here and figure out the total. So what's N here? 42 plus 36 plus 60 plus 8 plus 14, which is what?
160.
160. Thank you. So for A, guys, it's going to be 25% of 160, which is 40. For B, 25% of 100. You have to do this work, guys, even if you use technology. For C, what's C? 40%, which is 64. For D, it's going to be, what, 5%. It's 0.05 times 160, which is 8. And for F, it's going to be 0.05 times 160, which is 8. And if you guys add up those values, they should add up to 160 as well. Okay, so we're going to put them in L2. These are expected values in L2. So let's do this. I'll get the calculator ready. And here you go. Okay, I'm going to begin with L1 first. Always L1 is the observed values, guys. So we have 42, 36, 60, 8, and 14. L2. It's very easy test if you know what to do here. Just figure out the expected values and you're all set. I have 40, 40, 64, 8, 8. As you notice, guys, the difference between the L1 and L2, it's not substantial, 42 to 40, 36. So probably the observed values and the expected values did not change much. So probably we're not going to be able to say that the distribution has changed. We'll see. Okay, so now we go to Stat, Calc, Tests, scroll up, Goodness of Fit test. And here you go. L1, L2. Can a student tell me what the degrees of freedom are here? It's number of categories minus 1.
4.
4. Thank you. And let's hit draw if you like. See, I told you it's a right square distribution. Chi-square is 5.25. And the p-value is 0.2626. I told you we're not gonna reject HO. Put all in L1, E in L2, and run goodness of fit test. Degrees of freedom equals 4. So chi-square is 5.25. There you go. And p-value, guys, is 0.2626, which is bigger than alpha. So we fail to reject HO.
Mr. Benz, what was the degrees of freedom?
Oh, here's how you find the degrees of freedom. Good question. You count the number of categories. You have 1, 2, 3, 4, 5, and you subtract 1. So whatever number of items you have here, you just subtract 1. So I got 1, 2, 3, 4, 5, minus 1 is 4. And then conclusion, there is not enough evidence. What was alpha? At the 0.01 level of significance you can say to support the claim, or you can say to conclude that the distribution of grades has changed or is different than expected. So that means it's not different than expected. It's still the original distribution valid. And you can say there's not enough evidence to support the claim that the distribution has changed, the language that you are used to. But you might have to select this one from a drop-down menu. That's why I'm saying he might put the word conclude, which is okay. You can use this word as well. Okay, so this is one of the questions, guys, with section 10.1. Any questions about it? So again, all you need to find is the expected values, which are the percent of the total. I'm going to tell you the common mistake that students make, from my experience, teaching this course. Students know that they have to do something with the percent, but what they do for the 25%, they do 25% of 42, which is wrong. You have to do a 25% of the total, not 42. So you just figure out the total and do the percent of the total. Once you do that, put the observed values in L1, expected value in L2, and run a goodness of fit test. But don't forget about the degrees of freedom. And that's it. It's as simple as that. Okay. What I'm gonna do now, so I can I'm gonna go to section 10.4, and then we'll visit 10.3 later. 10.4 is an easy test. And usually students think of it as a freebie when I ask a question about section 10.4. So I want to do it first. Okay. What is section 10.4 is, and I'm going to give you guys a last chance for bonus credit. So you will have, just an assignment, one question from this chapter as an extra credit later. You'll get details from me via email. So 10.4, it's called one-way analysis of variance test. It's called ANOVA. Let me give you an example of this test. You learned in chapter 8 how to compare two means, mu1 and mu2. So if you have two population and you want to test whether one mean is greater than the other or less than the other or different, you can do that. But what about if you want to compare more than two means, three means or four means, if they are equal or not? Well, chapter 8 does not allow us to do that because chapter 8 is only about two samples. But if you have more than two samples, if you have a 3 or 4 or 5, we have what we call the one-way analysis of variance test to test if 3 or 4 means are the same. I'm going to show you some examples, guys, right away of what this chapter, this section is about. So just to have a feel of what we're trying to achieve in this section. Let me show you some examples. Here you go. This is one example. Number 5. The table shows the cost per ounce in dollars for a sample of toothpaste exhibiting very good stain removal, and very stain removal. At alpha, so you see you have 3 samples, very good, good, fair, more than 2 samples. At alpha equal 5%, can you conclude that at least one mean cost is different from the other? So we want to check, just if the average cost is the same or they are different. Here is another one. The table shows the prices in dollars for a sample of automobile batteries. You can see we have more than 2 samples. You have 3. The prices are classified according to battery type. At alpha equal 5%, is there enough evidence to conclude that at least one mean average battery price is different from the others? Here's another one right here. In a recent study, a health insurance company investigated the number of days patients spent at the hospital. You can see, guys, how many samples we have here. We have more than 2. We have actually 4. In part of the study, the company selected a sample of patients from 4 regions of the United States and recorded the number of days each patient spent at the hospital. The table shows the results of the study. At alpha equal 1%, can the company reject the claim that the mean number of days patients spent at the hospital is the same for all 4 regions? So you want to check if the 4 means are the same or they're not the same. Whether if you are in the Northeast region, Midwest, Southwest, South or West, it doesn't matter. Hospitals all have the same policy on the number of days, you can stay at the hospital. So these are the types of questions you're going to answer, and you will see the test is very, very easy test to perform. So here's the hint. When you see more than 2 samples in a question, it's an ANOVA test. It's section 10.4, which is going to be asking you to test whether the means are equal or one mean is different from the others. So what I'm going to do, guys, I'm going to walk you through some examples and how to perform this test. Okay. What does this test do? The one-way ANOVA test compares the means between the groups you are interested in and determines whether any of those means are statistically significantly different from each other. Specifically, if tests the null hypothesis. Okay, here is how you state the null and the alternative, guys, and you don't change that from one problem to another. HO should be mu1 equals mu2 equals mu3 equals mu4, whatever, how many. If he gives you 3 sets, you put means are equal up to 3. If he gives you 4, you put means are equal up to 4. If he gives you 5, you put mean equals up to 5. And HA, this is a language that you have to memorize, guys. At least one of the means is different from the others. So this is how you state the null and the alternative. In order to perform the test, the samples must be random and independent. Population have to be normally distributed. Means bell-shaped. And population variances, we have to make this assumption they are equal. If I ask you to perform this test, guys, you don't worry about those assumptions. That means you assume that they work. Now, in order to perform this test, we're going to be using technology, but it's a different distribution. It's the last distribution, guys. You learned about Z distribution. You learned about T distribution. You learned about chi-square distribution. We did that just earlier today. And the last distribution we'll be using to perform this analysis of variance stats, it's called the F distribution. And I'll show you how this F distribution work. The F distribution, just learn the definition, guys, but you don't have to worry about it much. You just use, just the program, that's built on the calculator. The F distribution is a family of curves. It changes with the degrees of freedom. It has 2 degrees of freedom, one for numerator and one for denominator. Because the formula of F is S1 square is over S2 square, so it has a numerator and denominator. And the curve, the shape of the curve, it changes with the degrees of freedom of numerator and denominator. It is skewed to the right. It's just like the chi-square distribution. So it's not symmetric. It's not bell-shaped. And I'll show you a sketch of total area under any curve is 1 always. And the values of f are always greater than 0. As you can see, guys, it starts from 0 and up. So it looks very much, just like the chi-square distribution, but it has 2 degrees of freedom, one for numerator and one for denominator. We're going to be using ANOVA test using the F distribution. And how do you use the ANOVA test? We input the data into L1, L2, L3, etc. We go to stat to test, and we pick ANOVA, and we input L1, L2, L3, etc. And then we run the test. We get 2 values, the test statistic, which is called F, and the p-value. And once you get the p-value, you make a decision to reject or fail to reject HO, whether if the p-value is less than alpha or more than alpha. Well, let me put this to practice instead of just talking about it. So we're going to do this exercise, guys. And if you have your calculator handy, please have it ready so we can do it together. So now, guys, you can see 3 samples. As I told you, this is a hint to you that you have to use right away. Once you see more than 2, you know it's ANOVA. ANOVA means one-way analysis of variance, ANOVA test. Okay, let's read it. A medical researcher wishes to try 3 different techniques to lower cholesterol levels of patients with high cholesterol levels. The subjects are randomly selected and assigned to one of 3 groups. You see, they're random and independent. Group 1 is given medication, Group 2 is given an exercise program, and Group 3 is given a diet program. At the end of 6 weeks, each subject's cholesterol level is recorded. Test the hypothesis that there is no difference amongst the means. Okay. Here's how you state HO, as I told you. So how far do I go here? mu1 equals mu2 equals what, guys? mu3, up to 3. 1, 2, 3. HA, at least one of the means. The language that I told you have to memorize is different from the others. Can a student tell me where the claim is? Is it HO or HA?
Would it be HO?
Yes, because he said there is no difference. No difference means equal, guys. Exactly, you are correct. Okay, let's do it. Turn your calculator on. You know, guys, you have to put the samples in the lists. The calculator need to know what's given to you. So this is going to go to L1, this is L2, and this is L3. Let's do that. That's why I told you it's an easy test. It's not difficult at all. You don't worry about the change in signs or anything. This is always assumed to be a right tail test. And you will see how easy it is to use the ANOVA test. But it is easy after you input the data into L1, L2, L3. This is L1, L2, samples don't have necessarily the same size, but it happened to have the same size here. It's not necessary. All right, and now, guys, quit and go to stat, tests. ANOVA is the last test on your calculator and under test, so scroll up. And I think, can you guys guess what I have to enter? I have to enter L1, comma, L2, comma, L3. second and number 1, second and number 2, comma, and then second and number 3. There you go.
Mr. Bazzi, where's the comma?
Oh, right here. Sorry, you didn't see it right here.
Okay, thank you.
Got it? I'll repeat it. I'm going to repeat it so students can see it. So stat, tests, up, ANOVA, and watch, guys. L1, second number 1, comma, right here. Without the comma, you'll get an error. Second number 2, and then second 3, and close parentheses. Okay, all you need, guys, is the first 2 values, F, which is the test statistic, and the p-value. So let me write them down. ANOVA, L1, L2, L3, 11.095 or 0.09. Usually F is 2 decimal places. And p-value I'm going to do 4, which is of course less than alpha 0.05. Reject HO. And conclusion, guys. We rejected HO and the claim is in HO, so there is enough evidence at a 0.05 level of significance to reject the claim that there is no difference amongst the mean. So that means there is a difference, guys. Now, which one is the one that's making a difference? We don't know, but there is a difference. That means the results are not very much the same. And you can see, guys, the group 2, it seems like the numbers are a lot lower than group 1 and group 2. That's why they're not the same. Turns out that they're not the same. Okay. Let's do another one. I think I have another one there. Yeah. A researcher wishes to determine whether there is a difference in the average age of middle school, high school, and college teachers. Teachers are randomly selected. Their ages are recorded below. Test the hypothesis that there is a difference in the average age of each group. Okay. HO, guys, will be mu1 equals mu2. HA, at least one mean is different from the others. And can you guys tell me what the claim is, HO or HA now? He says, test the hypothesis that there is a difference in the average age.
HA.
HA, I agree. If he says no difference or equal, guys, the claim is in HO. If he says difference, the claim in HA. Okay, this is gonna go to L1, L2, and L3. So we're gonna check if the ages are the same. So let's do that. Let's put the data in L1, L2, L3. So we put the data from the middle high school and college teachers in L1, L2, L3, and now we're gonna perform ANOVA test. So I'm gonna quit, stat, clear, stat, test. Scroll up, guys. ANOVA. And again, L1, comma. Let me show the comma here. Second 2, comma. Second 3, close. And enter. There you go. So F is 2.52 and p-value is 0.1142. ANOVA. And you get F, not T or Z, because this is an F distribution. Okay, this is bigger than alpha, guys. Fail to reject HO. Even if we thought that they were different, well, we couldn't say that they are different. So, conclusion, there is not enough evidence at the 0.01 level of significance to support the claim or conclude that there is a difference in the average age of each group. We could not conclude that there is a difference, guys. Although the data we're looking at, it could be a little bit misleading us to believe that probably there is a difference, but the test didn't reveal that. All right. So this is section 10.4. You should be able to work on it. Next time I meet with you guys, we'll do the remaining sections. And so for the time being, if you can work, just on problems from those 2 sections, that would be good.